Okay, we're back. We're going to do section 7.4, factorials, permutations, and combinations. And so what's going to be in this video, let me just put my notes here so I can see them. Well, obviously factorials, permutations, and combinations. So, part 1, what is a factorial, a permutation, and a combination, right? We have to be able to define what these things are before we can talk about that. And this first section would connect with these problems in section 7.4 and 55. The second part is permutations and the multiplication principle, actually, again, that we saw in section 7.3. Permutations are really strongly related to the multiplication principle. Multiplication principle. And in fact, permutations are really just the multiplication principle. And so that's problems 31 through 33. And then 3 is about combinations. That's the third part of this video, and that we'll deal with 41, 42, 61 through 66. And 4, card problems. Cards are a classic example of permutations and combinations, and in fact, gambling is really where this whole science of probability got started. The big question in the mid-1600s being, if you were playing a game and there was a big pot and the game had to be stopped for some reason, how do you split up the pot if the game hasn't finished? Okay, so part 1, permutations and combinations and definitions. So definitions. So permutations and combinations, what they deal with is that they're dealing with picking R things out of N, right? And so for an example, we'll just erase that. An example, 10m, let's see if I can get the and symbol right, and m's on a table. And you pick 7. How many ways are there to do that? Well, how many possible such combinations are there? And there's really 2 answers to this. The one is which, well, do you just grab them? Right? And what that means is order doesn't matter. You just pick all 7 of them all at once. Doesn't, oops. Right? And this would be called a combination. So imagine a pile of M&Ms or a bowl of M&Ms, and you just stick in your hand and you grab a bunch. And you open your hand and you have 7 M&Ms. If you just grab them, the order doesn't matter, that's called a combination. Pick them in order, right? Like first a blue one, then a green one, dot dot dot. Right here, order matters. And that's what a permutation is. Okay, and so there's the basic definitions. As we go through the section and the examples, you'll see the differences between permutations and combinations. In particular, problems 25 through 28 in section 7.4. (7.4), 25 through 28 are all permutation order matters, or combination. Right? These problems just ask, which one is it? And we're saying order, we're saying the order of the selections that's happening. Does that order matter? If you just grab a bunch of M&Ms and you pop them in your mouth, and it really doesn't matter what order they were picked in. If you grab M&Ms and you're like, okay, I'm going to eat the blue one first, and the green one, and then the red one, then the order matters, because obviously having a blue M&M and then a green M&M tastes better than having a green one and then a blue one, if you've eaten a lot of M&Ms. Okay, so order. Does order matter or not? If it matters, it's permutation. If it's a combination, it doesn't. 7, 4, 25 through 28 are asking that question. Okay. Next part of this first part of this video is about a factorial. And what are factorials? Well, these are yet another symbol of which we love in mathematics because it allows us to organize our thinking. And this symbol is an exclamation point. So 1 factorial is defined to be 1. 2 factorial, so 2 factorial, you read the exclamation point as a factorial, is 1 times 2. 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. And you can see how this is going. 5 factorial is 1 times 2 times 3 times 4 times 5. If you want to figure out what these numbers are, 2 factorial is 2. 3 factorial is 1 times 2 times 3. That's 6. 4 factorial is 1 times 2 times 3. Just to break those up a little bit. And we know that 1 times 2 times 3 is 6. So 6 times 4, that's 24. What's 1 times 2 times 3 times 4? Well, we know this here, right? 1 times 2 times 3 times 4, that is 4 factorial, which we just counted to be 24. 24 times 5 is 120. 6 factorial, you can figure that out. It'll be 1 times 2 times 3 times 4 times 5 times 6. So that's going to be 5 factorial times 6, which is 120 times 6, which is 720, etc. You should have on your calculator a button or something that you should have a button on your calculator that's got an exclamation point on it. That's the thing that calculates factorials for you. Okay. A nice thing about factorials is that they divide particularly nicely. What is 7 factorial over 4 factorial, for example? Well, it's 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. And that means I can cancel out those guys. 7 times 6 times 5, which is 210. So, if I'm dividing factorials, it works out pretty well. Some factorials are so big, like 807 factorial, that your calculator might not be able to do it. It depends on how fancy a calculator you have. But what's 807 factorial divided by 805 factorial? Well, it's easy actually to do this by hand. It's 807 times 806 times 805 times 804 times ... all the way down to 1, because that's what the factorial means. Take 807, multiply by every number less than it, divided by, well, 805 factorial is 805 times 804 times ... all the way down to 1. So, what's this division? You can cancel out these suckers, and you're left with 807 times 806. And if you multiply that out, it's 650,442. So division of factorials is pretty easy because almost everything cancels out. So, what does this have to do with permutations and combinations? Notation. PNR. Pick R things is a definition out of N things, order matters. So P and R, number, is this permutation, picking R things out of N where the order matters, and there's a formula for this, and that is N factorial over N minus R factorial. Okay, so if we go back to our M&M example, right? 10 M&Ms on a table, you pick 7, right? So you're picking 7 things out of 10. This is R. R is always the smaller number. Out of 10, that's N. If we're picking them one by one, right, this is a permutation. So if we're picking a permutation of 7 M&Ms, that's R, out of 10, that'll be 10 factorial over 10 minus 7 factorial or 10 factorial over 3 factorial, right? And if you divide that out, you'll get 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 3 times 2 times 1. This is 10 factorial, this is 3 factorial. These guys cancel out. You can multiply it all out, and you get P of 10 comma 7 is 604,800. Right? So if you're fastidious about your M&Ms and you want to pick the 7 out in order, you have 604,800 ways to pick 7 M&Ms out of 10. C and R pick R things out of N things where order does not matter. It's a combination. Right? And so this is people who just grab their M&Ms and eat them. So C, oops, sorry about that, got a little ahead of myself. CNR, the formula is n factorial over r factorial n minus r factorial. And so example C107, taking 7 M&Ms out of 10, 10 factorial over 3 factorial times 10 minus, oops, 7 factorial, sorry about that, or 7, 10 minus 7, 10 minus 7 factorial. So 10 factorial over 7 factorial times 3 factorial. And note that I should have parentheses around these because you take the factorial first and then you do the multiplication. So this is 10 times 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1, all over 7 times 6 times 5 times 4 times 3 times 2 times 1 times 3 times 2 times 1. So again, dividing factorials can cancel that out with that. 3 times 2, well, a 3 can cancel part of that 9. The 2 can cancel part of that 8. 3 times 4 times 10. 12, 10, 120. So there's 120 ways to just grab 7 M&Ms out of 10 if you're not worried about it. Okay. A thing to keep in mind about these formulas is that this formula and this formula you don't need to have memorized because your calculator should have a P&R, either a button or somewhere in the programmable part. It should be able to calculate both of these things for you. So you don't need to memorize these formulas. But they are related. What's the relationship between P&R and CNR? Well, if you notice, P is always bigger than C, right? There's more ways to order 7 things out of 10 than to just pick them. And note that P of 10, 7 over C of 10, 7, if you actually divided them, what would you get? It's 604,000, oops, 604,800 divided by 120. And in this case, I hope I wrote that down. It's a very large number, but what it turns out to be is 7 factorial. Right? And we actually picked 7 things, right? So if I take P107 over C107, I get 7 factorial. In general, well, let's actually, before we do the general, let's actually see why this happens. A permutation is a result of a two-step process, right? Think about picking 7 M&Ms in a particular order. One way to do that is just pick them in a particular order. First the blue one, then the green one, etc. Or, step 1, just grab 7 of 10, not in order. And how many ways is there to do that? Well, it's a combination. I'm just picking 7 out of 10, not in any particular order. And then the second thing is order the 7 M&Ms. Ooh, I think it was like that. Right? And how many ways are there to order 7 M&Ms? How many, if you got 7 M&Ms sitting on the table, how many ways are there to order them? Well, that's a multiplication principle. 1, 2, 3, 4, 5, 6, 7. How many choices do you have for the first M&M? 7. Once you've chosen that one, how many do you have for the second one? 6. For the third one, 5. For the fourth M&M, well, there's only 4 left. For the third one, there's 3. For the fifth one. For the sixth one, there's 2. And for the seventh, there's 1. Right? So if I need to order 7 M&Ms, I pick a first one, there's 7 choices for that, then I pick a second one, there's 6 choices for that, then I pick a third one, 5, dot, 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 dot. And we have a nice symbol for that. That's 7 factorial. So, a two-step process. How many ways are there to, how many outcomes are there of a two-step process? Right? And the outcome should be P107, but the first step is C107, right? Pick 7 of 10 unordered, and then times 7 factorial. And so that is ordering the 7 that you picked. And so that's why P107 over C107 is 7 factorial. Right? That's how to order 7 things. In general, P and R is actually C and R times R factorial. Also not a formula you need to memorize, but that's where some of these formulas come from. Okay, so that was a little bit about factorials and relationships between combinations and factorials. Permutations, so part 2 of the video. Permutations and factorials and multiplication principle. That's what it was, not factorials. And this is problems 31 through 33. Right? The classic permutation problem is a race of 8 people. How many possible finishes are there? And a finish is a first place person, right? And a second place person and a third place person. And it matters what order you're in. Right? If you're running a race, it matters a lot whether you come in first or second. Right? So this is a permutation. How many people are running? 8. How many people are we picking? 1, 2, 3. So P8, 3, and that is P8, 3, 336. Okay, or you can just do it as a multiplication principle. Right? First place, second place, third place. You can pick a first place winner, 8 possibilities. Pick a second place winner, well, you've already picked 1, so there's 7 possibilities for that. Pick a third place winner, there's 6. Right? And if you multiply those together, you get 336. Why does these 3 things equal that? Well, remember that the formula for the permutation is 8 factorial over 8 minus 3 factorial, which is 8 factorial over 5 factorial. This is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. Cancel that out, and you get the 876. So permutations, if you're wondering where these formulas come from, permutations come straight from the multiplication principle. Combinations come from knowing the formula for permutations and then using this factor to get that formula. Okay. There's not a whole lot to permutations because it's really just the multiplication principle, and knowing that if you're worried about order, if it matters what order you come in, then you use the permutations. Combinations, so this is the third part of this video. And this deals with a bunch of different problems. We'll start with 61, problems like 61 and 62. Actually the subcommittee problem. This shows up in a bunch of these problems in various places. So a subcommittee of 3 chosen from a larger committee of 15. And if you get into professional life, you'll be on committees so often your head will spin. Sort of the worst thing about having a job. So there's a committee, it's got 15 people, they need a subcommittee of 3 people, they're not worried about who's doing what, it's just 3 people got to go and do this thing. So order doesn't matter here, we just need 3 bodies. So this is C15-3. And if you grind that out in your calculator, you get 455. And now problems like 61 and 62, right? So suppose 24 donuts are delivered to a faculty meeting. And donuts are what meetings, handleable, are delivered to a faculty meeting. But 12 of them have coconuts on them. And some faculty members don't like coconut. So, how many possible ways are there for a faculty member to choose 4? Chooses 4 donuts. How many ways are there to do this? Well, apparently this faculty member isn't picking them in order, just choosing 4, so it's a combination. You're picking out of 24 donuts and you're picking 4. And how many is that? Well, 10,626. How many ways can this faculty member, who doesn't like coconut, pick donuts with no coconut? Well, now they're only choosing 12, right? Because there's 12 that have coconut, so 24 minus 12, there's a dozen that don't have coconut, and they pick 4 of that. And how many of those? 495. Right. So here the restriction of no coconut cuts down the number that we're choosing from 24 to 12. Okay. We can, like in problems 41 and 42, combine combinations with the multiplication principle. So suppose a bakery has 12 types of donuts, uh, 10 types of cakes, and 22 types of cupcakes. And the faculty are having a big sugar blowout for some reason, and so a faculty committee, I probably shouldn't do these videos just before I have dinner. A faculty committee chooses 4 types of donuts 2 types of cake, and 12 types of cupcakes for the meeting. Right? And so they're just saying, you know, these 4 types of donuts, these 2 types of cakes, these 12 types of cupcakes. How many ways can they do this? Well, it's a multiplication principle, right? It's a sequence of events. First they're choosing their donuts, then they're choosing their cake, and then they're choosing their cupcakes. So anytime you have a sequence of choices, we have a multiplication principle. So they pick first their donuts, and then they pick their cake, and then they pick their cupcakes. How many ways are there to pick donuts? Well, they're picking 4 out of 12, and they're not really worried about the order, so C12, 4. They're picking 2 types of cake out of 10, so C10, 2. And then they pick 12 types of cupcake out of 22, C22, 12. If you multiply all that together, it turns out that it's a very big number. In fact, it's 60,235,074,900. So there's that many ways. It would take a while if you, a lot of faculty meetings to go through all of those possible combinations, right? But, you know, it's a sequence of choices, and a sequence of choices means the multiplication principle. Now, card problems, 37 through 40, and secretly 56. Dealing with a deck of cards, and deck of cards again are sort of classic permutation and combination, well, combination kinds of problems. So let me lay out what a deck of cards looks like. There are 4 suits: hearts, let's get the red ones together, hearts and diamonds, and clubs and spades. And each suit has got 8, 9, 10, jack, queen, king, 13 cards. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, of diamonds, and then of clubs and of spades. These are called ranks. There's 13 ranks of cards. Aces are 1 rank, jacks are another rank, 5s are another rank. So there are 13 ranks. Right. There are 4 suits. There are 52 cards total. There are 26 red cards, 26 black cards, and jack, queen, king. These are called face cards. Lots of ways to carve up a deck of cards. Okay, so how many 5-card hands all clubs? Right, that's a reasonable question. Often many poker games you get dealt 5 cards, and so you're interested in, well, what's the probability that they get all clubs? Well, what do you have to do? You have to choose 5 clubs from 13. Note that the rest of the deck is kind of irrelevant. The fact that there's also 13 hearts really doesn't matter, because we're just looking for, I need to be able to pick 5 clubs, and there's only 13 clubs. So C13, 5. When I'm dealing with a poker hand, it doesn't matter what order the cards are dealt to me or what order I hold them in my hand. It's just what the total is. So the poker hands are always combinations. So C13, 5 is 1,280. 87. Okay. How many 5-card hands? Have 2 spades and 3 clubs. And now here's where you have to start thinking about these constructions of the hands as being a process. How do you get 5 cards that have 2 spades and 3 clubs? Well, think of it as this. First, pick 2 of 13 spades. And then second, pick 3 of 13 clubs. That's a sequence of choices. First pick the spades, and then pick the clubs, and then that tells you how many you have. So there's C13 2 ways to pick spades, right? 2 out of 13. And there's C13 3 ways to pick 3 clubs out of 13 clubs. And if you multiply that together, you get 22,308. Right? So a lot of these poker things is, can you look at the way the hand is described and break it down into a sequence of choices, and then you can figure out how many different hands there are that have that. So how many full houses are there? Right. And of course, if you're playing like 7 cards, then that doesn't, full houses doesn't matter. So what's a full house? 3 cards of one rank, 2 cards of another. Right. And remember, rank is aces is a rank, 2s, 3s. So if I had 3 10s and 2 6s, that would be a full house. Okay, so 3 cards of one rank, 2 cards of another. I need to think of this as a process to be able to count how many different full houses are. So what's the process? Well, first I need to pick the rank that my 3 cards will come from. And there's 13 possibilities. Once I pick that rank, I pick 3 out of the 4 cards from this rank. What's the third step? Well, now we move on to the other one. I need to pick one rank of 12, because I already picked one of the ranks, and so we don't want to use that one again, so we're down to 12 of them. And then fourth, well, we need 2 cards of that particular rank, so we pick 2 of 4 cards. Right? And these are all combinations. So first rank, 3 cards, and then you have to pick your second rank and pick 2 cards. Right? Picking 1 of 13, C13 1. Pick 3 of 4, so that's C4 comma 3. Pick 1 rank out of 12, so C12 1 comma 1. Pick 2 cards out of 4, so C4 comma 2. And if you multiply all that together, you get 3,744 possible full houses. Right. We can get a little more complicated with this. A 2-pair hand is 2 cards of one rank, 2 cards of another rank, and 1 card of a third rank. So 2 10s, 2 5s, and an ace, for example, or 2 queens, 2 jacks, and a king. So how many of these are there? Well, you can see how it's beginning to break down. I have to pick this rank and then 2 cards from that. Then I have to pick I have to pick a rank and 2 cards, and a rank and 2 cards, and a third rank and 1 card. Does it matter in which order I pick these 2 ranks? Right? And the answer is no, I just need to have 2 of them. So what's the process here? First, pick 2 ranks of 13. Second step, pick 2 cards from one of these ranks. Right? So you pick 2 ranks, say 10 and ace, and you pick 2 10s. Third step, pick 2 cards from the other of these ranks. And that gives me 4 cards now. I've picked 2 cards from one rank, 2 cards from another rank. And now I just need the 5th card, and the 5th card has to be of a different rank than the first 2. So 4th step, pick 1 rank out of 11. Remember, we already picked 2, so we're gone down from 13 to 11. And then 5th, pick 1 card from that rank. Okay, so we have 5 steps, 2 ranks out of 13. That's C13-2. 2 cards from one of those ranks. Well, there's 4 cards in a rank, so C4-2, and then C4-2 for the other one. Pick 1 rank out of 11, and then pick 1 card from that rank, C4-1. And you multiply all that together, and it becomes 123,552. Okay, so card problems, you know, they get a little complicated, but think about them in terms of picking a rank and then picking a number of cards from that and thinking about how many you have to do them. Okay, and so one last example. Suppose you have 10 people in a committee. And you need a 4-person subcommittee. But you know that Roger, Sarah, Jim two of these people have to be on it, but not all 3. Right? So, how many different ways are there to put this together? Well, you need to pick 2 of these 3. Right? And then, well, you need to pick 2 more. But how many people do you have to pick them from? Well, you pick 2 of those. That gives you 3, but out of 10, so there's 7 people left. This is Roger, Sarah, Jim, other people. So C7-2 and C3-2. And if you multiply that, that's 105.